So we've got an airplane that's traveling 1,001 meters above the ocean, and it's flying at 125 kilometers per hour, and it's going to drop a box of supplies to some shipwrecked victims below. Okay, you want to know how many seconds before being directly overhead should the box be dropped, and what is the horizontal distance between the plane and the victims when the box is dropped? Now, of course, we're being really nice in this problem because we're dropping a box of supplies to shipwrecked victims, but the main application of this problem, at least during World War II, was to drop bombs on the enemy. It's the same problem. Okay, it's just... So let's use a good problem-solving technique here. So set up the problem with given, find, and solve. Okay, so try and do that on your own. Pause the video, do it on your own, then watch. So here we've got an airplane, and I'm just going to draw a little airplane like this, put wings on it, like it's a supersonic airplane or something. And it's going to drop, and how fast is it going? Well, it's traveling, here's its velocity, is 125 kilometers per hour. That's actually pretty slow. It's probably like a little Piper Cub, but it's easier to draw a jet. Now, you're way above the ground. So here's the ocean. You can draw a little desert island here with palm trees if you want to. Okay, but here the delta y here is 1,001 meters. But here's the thing about this delta y. Here's the box. Let's draw the box of supplies right here. When the box is released, what is its velocity? Well, this is really the initial velocity of the box in the x direction, right? The box is moving at 125 kilometers per hour horizontally the moment it's released. What is its initial velocity in the y direction? V naught y. What is V naught y? What is the initial velocity of this box the instant it's dropped? It's 0. It hasn't had time to fall down yet. So its velocity is 0 in the y direction. And it's going to come all the way down. And so now it's going to follow this trajectory, and it's probably going to take out these victims. Okay, here's the... So you really don't want to drop it right directly on them. You can lose your job. Okay, so... Okay, it came to that. So, what are we trying to find here? We want to know the time it takes for this to fall. And then for part B, we want to know what's the horizontal distance between the plane and the victims when the box is dropped. So here's when the box is dropped. So really we want to know delta x. From here, here's the box was dropped, and so it goes this far. And what do we know about delta y? Really, it's 1,001 meters, but it's really down. So we got to make that negative. So let's solve. So try and solve it now. Let's solve for A. What do we know? Well, we want time, but we can't really use the horizontal direction because we don't know delta x. That's two unknowns. So we have to look in the y direction. We know the initial velocity in the y direction. We know what the acceleration is in the y direction. And we know the displacement in the y direction. And we're solving for time. What has those four things in it? You look on your list of kinematic equations and you say, oh, okay, we don't know the final velocity in the y direction, and we're not trying to find it, at least not in part A. So that's the third kinematic equation. Delta y equals v naught y times t plus 1/2 a t squared. Now v naught y is 0. Solve for t. T equals multiply both sides by 2. So that's 2 delta y, divide by a, and then you take the square root. This is the most common equation we end up using when we're solving for time. But start with basic principles, our kinematic equations. Plug in our values, 2 times, now you got to put in the negative, and we know this is negative 9.8. Okay. Now, if you're watching this online, some people are, stop the video as often as you can and try and finish it yourself. Only use this video to get unstuck. So now we can multiply. We can go, okay, 2. Whoops. Okay, when I do that arithmetic, I get 14.3 seconds. It's quite a long time. But that's pretty high altitude. Now, let's do part B. Now, the problem with part B, well, okay, delta x equals v naught x times t. Now we know t. Here, we know the time. If the bell rings, you're free to go. I'm going to finish this. Can you be as quiet as possible? Let me finish this problem. Now, v naught x is 125 kilometers per hour times a time of 14.3 seconds. Well, nothing cancels here. Let's do it in meters. So we got to do unit conversion. Get rid of kilometers. 1 kilometer is 1,000 meters. Get rid of hours. 1 hour is 3,600 seconds. Whoops. So that cancels that. Hour cancels hour. Let's do the arithmetic. $125. And you get a delta x, a horizontal distance of 497 meters. Okay? Perfect timing! Let me zoom out, take a look at this thing, the whole thing. There you go. Very nice.